Okay, guys, let me go ahead and share my screen just so I can briefly go over our goals for today. Okay, so this is fourth period. Of course, we're in the third 6 weeks. Today is December the 2nd, and it is a Wednesday. Okay. Now, today is going to be a pretty straightforward day. What we're going to do, we're going to go over these notes as a class. These notes deal with types of forces. Excuse me. Basically, all the common forces in nature that you will see in a Physics 1 class, we're going to go over today in detail. Now, some of these forces we've already talked about before, but today I just want to focus on all of them just so you guys will know how to recognize them in any situation where they appear. So we're going to spend time going over these notes. So please be sure to ask any questions. If I go over something that you do not understand, don't hesitate to stop me because once we go over these notes, then I'm going to open the assignment, which is called Types of Forces. And basically, it's all multiple choice, and you guys just how to recognize when these forces appear in the real world. So the assignment is about 18 multiple choice questions. So it shouldn't take you too long to do it. Again, like I said, the goal for today is to get through the notes, then I'm going to make the assignment available to you all. Okay. Now, if you remember on last class period, and I briefly want to review the important points from last class period because some of those questions could be on the assignment that you guys are going to see later, that you guys are going to do later on. On last class period, we talked about free body diagrams, and we talked about how to interpret free body diagrams. So in other words, if you look at a free body diagram, you all need to be able to recognize what's happening to the motion of that object, whatever motion that that object is depicting. So let me pull up one of these video clips from last class period. Okay, so if you guys remember, on last class period, we watched this video clip of this young lady. Her name is Lexi, and she's bungee jumping. Okay. And last class period, we looked at her motion, and we drew a free body diagram that is representative of the forces acting on her. And we decided to look at what's happening in each situation. So remember the most important thing that I told you guys to remember from last class period. If you have an object and that object is moving in the same direction as the dominant force acting on that object, then that object is speeding up. If the object is moved opposite direction of the dominant force, then that object is said to be slowing down. Okay, it's something that you guys need to remember. Okay, that's something that we talked about. So, for instance, so in this situation right here, we see Lexi, she's bungee jumping, and here the dominant force acting on her is gravity. So, in this moment here, she's going to be speeding up. Now, as she gets closer and closer to the river, notice there's a rope that she's connected to, and this rope begins to tighten. And as this rope tightens, we've introduced another force here, and that is the force of tension. So let me draw out these forces for you all. So there's a force of tension here. And there's also a force of gravity. So gravity is pointed straight downward. And then there's also another force here, which is tension. And tension here is the dominant force. So because tension is the dominant force, I'm going to draw this arrow larger than this arrow here. Right? So the larger the arrow, the greater the magnitude of force. Okay. So in this situation right here, guys, notice Lexi is moving opposite the direction of the dominant force. So she's clearly going to be slowing down here. Okay. You guys know she slows down because she doesn't fully go into the water. In fact, she slows down, briefly comes to a stop, and then she starts coming back up. Okay. Someone tell me, as Lexi is coming back up, what is going to be happening here? Will she be speeding up or slowing down? So while she's moving in the positive direction, anyone? What's happening? I'm sorry.
Speeding up.
Exactly, Aaron. She's going to be speeding up. Exactly right. And you know she's speeding up because she's moving in the same direction as the dominant force. Guys, if there's one thing that you all remember from last class period, please remember that. That is super important. If the object is moving in the same direction as the dominant force, it's going to be slowing down. If it's moving in the opposite direction of the dominant force acting on it, it's going to be speeding up. Okay. So in this case, it clearly makes sense that she's going to be speeding up coming out of the water because the tension force is pulling at her. Right? So she's acting in the direction of the dominant force. Okay? So just something from last class period that I wanted to go over that is going to be very important in the future. Okay. Now, before we start going over those notes, there's also something that I want to go over that we mentioned before Thanksgiving break. So, if you guys recall, before Thanksgiving break, I talked about weight. So, imagine this is me here in red. So this is me, and I'm standing here, and pretend there's a scale right here, and I wanted to know my weight. So if I want to know my weight, I'm going to stand on the scale, and the scale is going to read off my weight. Well, the question is, how does the scale works? Well, guys, remember what I said several weeks ago. A scale works, excuse me, a scale works by indirectly measuring the magnitude of the gravitational force, right? That's what the scale measures. The scale measures the force of gravity pulling on it. And that makes sense, right? Because as gravity, so in this situation right here, so as gravity from the Earth pulls me down toward the center of the Earth, that force is what's pulling me on the scale. So that force is causing me to press against the scale, which is converting those numbers into a weight. Okay, so this force here, the force of gravity, is what the scale is reading. Okay. So remember we said the last time, force of gravity is equal to an object's weight. Okay, because that's what the scale measures. The scale indirectly measures the force of gravity acting on the object. Okay. And guys, suppose my mass here, my mass is 75 kilograms. Okay. So if my mass is 75 kilograms and I want to know my weight, I just use the equation for the force of gravity, where it's understood that the force of gravity is equal to the object's mass multiplied by 9.8. Okay. And of course, guys, I want to round 9.8 off to 10 in order to make my calculations easier. So mass times 10 is the equation for the force of gravity. Okay. So someone tell me, if my mass is 75 kilograms, what is my weight? Anyone? Here on Earth. What is my weight here on Earth?
Wait, how do you calculate the weight again?
Mass times 10.
750.
750 exactly. And what are the units for that, Stephanie? Anybody? What are my units for weight in physics? Do y'all remember? Well, newtons, exactly.
Oh.
Yep. Right, because weight is equal to the force of gravity, and the units for force are just newtons. So exactly. So my weight is 750 newtons. Okay. All right, guys, just keep that in mind because there's going to be some questions on the homework for later on where you guys will have to calculate the weight of an object if you know its mass. So you just multiply mass times 10. And guys, in physics, we typically describe weights in newtons. Of course, in your everyday life, you're used to using pounds, but in physics, we use newtons for weight. Of course, you can easily convert back and forth between the two. There's a conversion factor between newtons and pounds. Just know that in this class, we typically write weight in newtons. Okay. So remember that, guys. Anytime you want to know an object's weight, that's just equivalent to the force of gravity acting on the object. Okay. Because that's what the scale measures. Anytime you step on a scale, the scale indirectly measures the force of gravity acting on you. Oh, and one thing I want to say here, guys, is that weights is something that can change if an object changes its location throughout the universe. So, for example, if I was standing on Jupiter, my weight would actually be larger. And that makes sense because Jupiter is a larger planet than the Earth, and so it has a stronger gravitational pull. So if I was on Jupiter, my weight would be a lot larger. If I was on the moon, my weight would be a lot less because the moon will be pulling at it and pulling at me with a smaller magnitude of force. Okay. Now, also remember what I said several weeks ago. Mass is something that can change from place to place. I'm sorry, mass is something that does not change from place to place. Weight can change, but mass does not. Because remember what mass means. Mass represents the total amount of stuff that makes up an object. And that doesn't change. Okay. So the total amount of stuff that makes up an object doesn't change. Like my mass is the same here as on Jupiter, as on Venus, as on the moon, anywhere I may go. What changes is my weight, because weight depends upon the force of gravity. Okay? Even though my mass is the same here as it is in the Andromeda Galaxy, my weight could be different because the gravitational pull is different there. Okay? So hopefully that makes sense to everybody. Okay. Let me go ahead and share my screen again and go back to Schoology so we can look at these notes for today. Like I said, the goal for today is just to go over all of the forces that you're going to see in a typical Physics 1 class, okay, and understand how to recognize where and when those forces appear in nature, okay. And again, some of these forces we've already talked about. This first force right here, the force of gravity, we've already talked about this a lot in this class. Obviously, we just got done talking about it. But one thing that I want to say in addition to this, guys, I know that in this class, we typically think of gravity as being the force that's acting between us and the Earth, right? Because the center of the Earth is pulling me toward it. Okay, so there's a gravitational force of attraction between me and the Earth. But the important thing that I want you guys to know is that the force of gravity, it is a universal force, meaning that it acts between any and all masses in the universe. So anytime you have two masses, you can guarantee there's a gravitational force of attraction between those two masses. So, for example, guys, in my hand, I'm holding up two balls here. I have a yellow ball and I have a red ball. So we'll call this mass 1, this is mass 2. Okay. Guys, believe it or not, Isaac Newton tells us that there's a gravitational force of attraction between these two masses. Okay. Now, it turns out that force is extremely small because these masses are small. Obviously, relative to something like the Earth, it's a small mass. So the force of attraction is small, very, very, very small. That's why in our everyday lives, we're not used to detecting this very small force. But just because it's small doesn't mean that it doesn't exist. It exists. We know it exists. We've measured it. In fact, gravity is the smallest force in nature. It's so weak that, again, that I said, in everyday situations, you guys don't really detect it. But guys, suppose that I was in outer space. Suppose that I was, far away from the Earth, and these two objects here, these two balls, were the only thing floating in space. If I set these two balls next to each other, believe it or not, they'll slowly drift toward each other because of the gravitational pull between these two balls. These two balls are literally pulling on each other. Because of that weak gravitational force that exists between them. Now, obviously, here on Earth, we don't detect it because it just so happens that these two balls, they are pulled more toward the Earth than they are toward each other. But the key thing I want you guys to know is that they exist. Again, you can think of the gravitational force as being very similar to the magnetic force. Everyone in here has played with magnets before in magnetic material. So just like there's an attractive force between the North Pole and the South Pole on a magnet, there's an attractive force between any and all masses in the universe. So, uh, so these magnets are drawn to each other. They're attracting to each other. And of course, one difference between the magnetic force and gravity is that the magnetic force is a lot stronger than the gravitational force. Like I said, the gravitational force is the weakest force in nature. You guys are used to being able to detect the magnetic force because it's so strong, even if you guys aren't used to detecting a gravitational force. Now, one more thing I want to say about this gravitational force is that this gravitational force depends very much on distance. So, in other words, when the two balls are close to each other, the gravitational force is relatively strong. When the two balls are far from each other, the gravitational force is relatively weak. Okay, so the closer the two objects get, the stronger the force. The further they are, the weaker the force. And again, you guys are familiar with that concept with magnets. As the magnets get closer together, so as they get closer together, you can feel that the force gets stronger, right? There's a strong pull. But if the magnets are far apart from each other, the force is weak. Okay, so the closer the objects get, the stronger the force. Okay, so similar thing with the gravitational force as we see with the magnetic force. Okay. So hopefully that makes sense. Okay, let's move on to talking about the next force in this class, which is what is known as the normal force. We've already talked about this force as well. The normal force. So this force is caused by two objects in direct contact with one another. It results from one object pressing against the other. It is always perpendicular to the surface of contact between the two objects. So, for example, come on, open up, baby. Come on, open up. Okay, and again, we talked about this several weeks ago when we talked about the normal force. Imagine that I have a box here, a blue box sitting on a table here. Because this box here is in contact with this surface and is pressing against it, there's a normal force between these two surfaces here. So not only is the blue box pushing down on the table, but the table is pushing back up on the blue box, right? So there's a normal force. So there's a normal force from this surface pushing upward on this box here. And again, remember, the normal force is always perpendicular to the surface of contact. So in this case right here, the normal force points straight up, right? So the surface here is pushing up on the blue box. If I want to determine what are the forces right now acting on this blue box. So there's gravity pulling down, but there's also the normal force pushing up. And again, like I said, guys, keep in mind the normal force is always perpendicular to the surface of contact. So let's say, for example, I have a situation like this where I have an object sitting on an inclined plane, as you guys see here. So where would my normal force be pointed here? Well, remember what I said, the normal force is always perpendicular to the surface of contact. So since this right here is my surface of contact, the normal force points like this. Come in. Yes, sir.
Taylor, can you tell me how the info is going to work on Friday?
Yeah, it's I can help you get it set up.
No, I mean, one of the students is asking me. They've never done one before.
Oh, all you do is just go into Schoology and just watch the video and answer the questions.
Okay.
Yeah, it's going to be self-explanatory in Schoology.
Okay.
Yeah. Okay, guys. Yeah, sorry about that, guys. Another teacher was asking me a question, but anyway, guys, since my surface here is at an angle, it's slanted, so the normal force here gets slanted as well. Is since this is the surface of contact, it has to be 90 degrees relative to the surface. Similarly, a similar thing is here. Suppose I had a book here, and this book was being pressed against this wall here. If I wanted to know the direction the normal force from the wall acting on the book, where would that be pointed? Well, in that case, the normal force will be pointed like this. Because again, it has to be perpendicular to the surface of contact. So the wall will be pushing on the book like that.
I don't know. Maybe to get that money. I mean, I
Hey,
already know he got money, but
Jerry, could you mute yourself? All right, so let's move on to something else. Let's see. Oh, and one thing I want to say, guys, the normal force is always a pushing force. It's a pushing force. Yeah, you're good, Jerry. I hear you got that money, Jerry. That's what I hear. You wouldn't mind sharing some of it? All right, guys. Oh, one thing I want to say here: the normal force is so since it's always a pushing force, just know that there's something different from the force of tension, because the force of tension is always a pulling force. So that's one difference you guys need to know between the normal force and tension. One's a pushing force, the other is a pulling force. And again, we're going to talk more about that when we get to that. Okay. When we get to tension. Any questions on the normal force before we move on? Okay. Now, let's talk about the force of friction, or the frictional force. Now, the frictional force is the force exerted by a surface on an object as the object moves across it or makes an effort to move across it. So anytime, guys, anytime you have two surfaces and those two surfaces are sliding across each other, you're going to have a force of friction there between those surfaces. And it's important to know that friction always acts opposite the direction of motion. So let me give you guys an example of what I mean by this. Okay. Guys, consider this example here. Notice what I'm showing you guys. I'm showing you guys an animation of, a video clip of a block sliding across a wooden surface. Okay, so this block here is sliding across the surface. So because the block is sliding across that surface, there's clearly a force of friction between the block and the surface. Okay, so the important thing that you guys have to know is that friction always acts opposite the direction of motion. So, guys, look at this block here. So if I wanted to know the frictional force right now acting on this block, I would need to look at its direction of motion. Can someone tell me, guys, if I had to draw the arrow for the frictional force, where would that arrow be pointed on this video clip? Would it be pointed to the left or to the right?
To the left, right?
Exactly, to the left. You got it. So if I wanted to know the frictional force right now, acting on this block, it will be pointed to the right. Thank you, Jeremiah. I'm sorry, to the left. To the left. It will be pointed to the left. So guys, remember that for the assignment later on, remember friction acts opposite direction of motion. Okay, so since the box is sliding to the right, then the frictional force acting on the block must be acting toward the left. Right? So in other words, there's some sort of friction there that's resisting this motion because it's sliding across that surface. Okay? So something you guys need to remember, friction always acts opposite the direction of motion. Okay. Okay. All right, let's move on. Okay, so we talked about the force of friction. It's a friction acts opposite direction of motion. Now, let's talk about air resistance. Air resistance is a special type of frictional force that acts upon an object, that acts upon objects as they travel through the air. So this is something we've already talked about in this class, that that air resistance acts upon objects as they travel through the air. And this is something that we talked about when we watched my skydiving video. So let me briefly put that on just one more time, just so we're clear on what air resistance is. Okay. So last class period, I showed you guys this video here of me jumping out of an airplane. Okay. Now, guys, everybody can clearly see that as I'm falling, there's clearly air resistance acting on me. And guys, air resistance is also a force that acts opposite direction of motion. It's a special type of friction. And y'all can clearly see that here. Notice how I'm moving downward, but if I'm moving downward, there must be air resistance. There must be air resistance acting upward on me. And everybody can clearly see there's a force acting on me that's acting upward, that is air resistance. And hopefully that should make sense of why that is, how you know air resistance acts opposite direction of motion. Because guys, notice as I've moved downward, I'm slamming up against these air particles. So these air particles are hitting my body and they're resisting my motion. So air resistance is acting upward as I fall downward. Okay. So just something you guys need to remember about air resistance. Air resistance is a special type of friction that acts opposite the direction of motion. Okay. Okay. Let's go back. All right, guys, so we have one more force to discuss on this page here, and then we're going to conclude the day on the back by just talking about various types of friction. And then I'm going to let you guys go so you guys can do your homework as soon as we get done with this. Okay, now let's talk about tension, the tension force. Okay, so it is a force that is transmitted through a string, rope, cable, or wire whenever it's pulled tight by forces acting from opposite ends. So guys, the key thing y'all need to know that anytime you have an object and you see a string, rope, cable, or wire, or something like that connected to it, you're going to always have a tension force acting on the object. So, for example, guys, give me just a second while I open up this file here. So consider this example here, guys, where this pulley here is pulling on this bucket of water. Okay, so if I wanted to know the forces right now acting on the bucket of water, right now, so I'm gonna circle the bucket of water here because I want to know whether the force is acting on the bucket of water. So if I want to know the forces acting on this bucket of water, okay. Well, guys, it turns out we know there's two forces acting on this bucket of water right now. There's gravity pulling downward, but there's also another force. Notice it's connected to this rope here, so there's clearly a force of tension pulling it up. Okay. And of course, tension is always a pulling force. So remember that. Tension always pulls on your object. Remember, the normal force pushes on your object, but the tension force pulls on your object. Okay, so this rope is literally pulling up on this bucket. Oh, and by the way, of course, you guys know that if the rope is pulling on the bucket, then according to Newton's third law, the bucket must be pulling on the rope as well. So those forces are equal and opposite. Um, what about here? What if I wanted to consider the force of tension, here acting on this brown block here, right? Because this brown block is also connected to a rope, so clearly there's a tension force acting on it as well. So that tension force will look something like this. So there's a force of tension pulling up on the brown block. Okay. But again, guys, remember, according to third law, if the block pulls on the, if the rope pulls on the block, okay, and the block must also pull back on the rope. So, for example, if I wanted to look at this tiny piece of the rope here, like this tiny piece, okay, if I wanted to know the tension force acting on that tiny piece of rope there, well, remember, if this rope pulls on the block is also pulling on the rope. So that means that there's also a tension force pointing straight down like this that's acting on the rope here. Because that's just Newton's third law. If one pulls on one object, then the other object pulls back. It just your direction just depends on whatever object you're looking at. Okay. Let's look at another example that involves the tension force. Okay, guys, imagine two people playing tug of war. This is a game that you guys are all familiar with. Okay. So if I wanted to consider the force right now acting on this guy, and only this guy. So if I want to know the horizontal force acting only on this guy, what would that force be pointing? Remember, this guy here is pulling on this guy, so the tension force will look something like this. Okay, right? Because tension is always a pulling force. So if I want to know the force acting on this man right here on the left, the tension force points in that direction. But guys, remember, according to Newton's third law, if this guy pulls on this guy, then this guy must also pull back with an equal and opposite force. So, for example, if I wanted to know the tension force right now acting solely on this guy right here, right? So if I want to know the tension force acting on him, then I would draw the arrow pointed like this, because again, tension is always a pulling force. Okay. So because this guy is pulling on this guy, the tension force must be pointed like that, right? So if I want to know if I want to know the force acting on the guy on the right, that's how my tension force will look. Tension is a pulling force. So anytime you have an object that is connected to some sort of rope or string or wire or something like that, you're going to have a tension force involved, and the tension force is always a pulling force. Remember, the normal force is a pushing force. Tension is a pulling force. Okay? So hopefully that makes sense. All right. Now, the last thing we're going to talk about today, I'm just going to finish these concepts on the back of these notes here, is I just wanted to go into detail with the various types of frictional forces you're going to see in this class. Okay. So in this class, guys, there's two main types of frictions you need to be aware of. You need to be aware of what is known as the static frictional force, and also what is known as the kinetic frictional force. So what static friction is? Static friction is the force that resists an object while it is at rest. It is the force that must be overcome in order to start motion. Okay. Kinetic friction is the force that resists an object while it is in motion and slide against the surface of another object. Okay. So in a nutshell, guys, static friction is the force that acts on your object while the object is at rest. Kinetic friction is the force that acts on your object while the object is in motion. That's the important difference between the two. Okay. So I'm going to read that again. Static friction is the force that resists an object while it is at rest. It is the force that must be overcome in order to start motion. Let me give you guys an example of what I mean here, just so everybody is clear on the difference between these two. So that whenever you do the assignment later on, you guys have a clear understanding of what I'm talking about. Okay, guys, so just so you guys are clear on the difference between static and kinetic friction here, I want you guys to imagine here that this man here is trying really hard to push this rather large box here. So this is a pretty large box. So, guys, as he attempts to push this box, he notices that the box isn't going anywhere. Okay, now the box isn't going anywhere because there's a force resisting it. That force is static friction, right? So as he push and he push and he push and it doesn't go anywhere, we know there's something resisting it. So remember when I said static friction is the frictional force that resists your object while your object is at rest. So because he's pushing it and it's not going anywhere, the box is still at rest. There's a static frictional force here acting on the object, which is what I'm going to draw now. So, so there's clearly a static frictional force. So I'm going to draw a static friction force. Let me draw this better than this. So there's a static frictional force acting here because the box is at rest. So in other words, guys, static friction is the force that must be overcome in order to start motion. Okay. Now, this guy, if he pushes and pushes and pushes, eventually he can push hard enough to where this box begins to slide. Okay. Now, guys, at the point that the box begins to slide, that's when kinetic friction kicks in. Okay. So everybody got that? So if he pushed hard enough and it slides, now that it's sliding across the surface, that's when kinetic friction is acting on our object. Okay, so right now, kinetic friction is acting on the object. Okay, so while the object is in motion, okay, we have kinetic friction acting on our object. And remember what I said, kinetic friction acts on our object whenever it's in motion. So as long as this box is in motion, as long as it's sliding, kinetic friction is what's acting on it. But when it's at rest, so when he pushes it and it doesn't move, static friction is acting on it. But once it's in motion and it's sliding, then we have kinetic friction. So guys, that's the important difference between the two, between static and kinetic friction. Okay. Static friction resists an object while an object is at rest. Kinetic friction resists an object while an object is in motion. Okay. All right, we're almost done here. Okay, so say that again. Static friction is the force that must be overcome in order to start motion. Kinetic friction is the force that resists an object while it is in motion and slides against the surface of another object. Now, we've already talked about air friction here. Air friction is just another word for air resistance. And guys, remember what I said before, air resistance is a special type of friction. And the reason why we say it's a special type of friction is because, remember, friction is a force that resists an object's direction of motion. So, as we saw when we were skydiving, as I was moving downward, air resistance was acting upward because air resistance is a force that resists an object's motion. But air friction specifically acts on an object while an object is traveling through the air. So, like in the case of your skydiving, whenever you're in free fall. Okay, so So just remember that, guys. Air resistance, or in other words, air friction, is a special type of friction. And you know it's a special type of friction because it acts opposite the direction of motion. Okay. Now, one more thing I want to discuss here when going back up to the top here, whenever talking about static and kinetic friction, both static friction and kinetic friction depends upon the roughness of the surface. So because of irregularities on surfaces, objects grip to the surface of other objects whenever they move across one another or attempt to move across one another. So guys, this is basically what I want you guys to understand, that static and kinetic friction is caused by roughness in surfaces. So for instance, again, examples always help. Guys, imagine this example right here where I have a really large crate that is, well, I have a large crate that is sliding across the surface of this wooden table here. Okay. Um, so, guys, what is it that causes the force of friction? Well, remember what I said, friction is caused by irregularities in the surface. So, here's what I mean by that. Imagine I could zoom in at this contact. So imagine that I can zoom all the way in here at this contact point between this surface and that surface. If I can zoom into this contact point. So imagine I was like a little ant and I could see that small. At that point, this is what I would notice. I would notice irregularities in the surface. I would notice bumps and grooves. And these bumps and grooves are actually the cause of friction, right? So because of these irregularities in the surface, as one object goes to slide across the surface of another object, it makes it difficult to do that because of those irregularities. In other words, these irregularities, you can kind of think of them as, allowing the objects to grip, basically to grip one another. And that gripping is what causes friction. So basically what I'm trying to tell you guys is that the rougher the surface and the greater the force of friction between that object and the surface of another object. Now, um, and obviously that would mean the smoother the surface, the less friction. For example, consider ice. If you go to slide across ice, you guys are very experienced with the fact that there's very little friction on ice, right? Because ice is a relatively smooth surface. So because it's a relatively smooth surface, you don't have as much irregularity. So there's not that much friction on ice. Now, I want to say this, ice is not entirely smooth. It's not perfectly smooth. So there's going to be some friction involved, even if it's just a little bit. Well, even if it is just a little bit of friction. In fact, guys, there's no such thing as a surface that is 100% smooth. There's no such thing in nature of a surface that is perfectly smooth. It does not exist. Now, NASA came close to building some smooth some nearly perfectly smooth spheres like several years ago. They came close, but again, it's just not possible in the real world to get something that is perfectly smooth. That's not possible. Nothing is 100% smooth. So every surface always has some type of friction on the surface, even if it's just a little bit. So obviously ice is relatively smooth, so there's not a lot of friction on ice. But like compare that to sandpaper. So sandpaper is very rough. So if you try to slide something across sandpaper, you're going to get a lot of friction in that case. All right. So I think we've covered enough for today. So remember, those notes are in Schoology. If you guys need to go back and look over them whenever you are working on your assignment. Also, I am going to post this video on my YouTube page as well, so you guys can look over that if you want to. Okay. Are there any questions for me? Any final questions before we end this Zoom call? All right, if there are no final questions, you guys are free to go. I will have the assignment open soon. Have a good day, everyone. Peace.
How many attempts are on the test? I mean the assignment.
2.
All right. I like that.
All right.